Hey guys, how are you doing? Today I'm at the math contest, and so we're going to still move forward with curve sketching, which is we got some really pretty awesome stuff that we're going to do. Now, what I'd like for you to do first is turn in your books to page 186, okay? On page 186, you are going to be looking at problems 1, 4, 6, and 7, okay? So what I would like you to do is answer on number 1, one interval for each part. Answer on number 4 and 6 and 7 where the function is increasing and decreasing. You will be do this most easily if you'll use interval notation. Please pause the video now, take 2 minutes, and then restart the video to check your answers. Okay, if you've restarted the video, what I'd like to do is for you to look and check your answers. So take a look at the answers for problems 1 and 4. Notice on problem 1, I assumed that the domain was 0 to 10 and didn't go any further than the actual picture showed. But on 4 and 6 and 7, because those graphs went with equations that were given, I acted as if the graph stretched further to the left and right, actually stretched to negative and positive infinity. So how'd you do on number 1? How'd you do on number 4? Do you need to pause the video and talk about this, make corrections, that kind of thing? If so, just do that. Pause the video and then make your corrections. Check number 6. How'd you do? Again, if you need to pause the video, talk these over, try to make things right, do. And number 7. Okay, I hope you've had time to check your answers. On each of these, you were just answering the questions visually from what you can see. What we're going to do now, though, is go back to 4, 6, and 7 because we have equations, and we're going to pound through the work algebraically so you know how to curve sketch using derivatives, critical values, sign charts, and in particular the first derivative today. Tomorrow, when I come back, we're going to do more of this, and we're going to add on this second derivative part of the work. So today, we're going back to 4, 6, and 7. The first thing we're going to do is find f prime of x. From f prime of x, we're going to find critical values. Once we have the critical values, we're going to do sign charts using f prime of x and making inferences about f of x. Then we will answer questions algebraically speaking about where a function is increasing and decreasing. We'll from there be able to name the x values where we get maxes and mins, local extrema. Then we'll plug the x's in to find the corresponding y's so that we can name the maxes and mins as points. So go back with me here to problem 4. So when you look at problem 4, forget anything you've already seen. So in fact, I'm going to cover this up so you're not looking at that again. So on problem 4, when I look at it, it says that y equals negative x plus 1 quantity squared. I need to take the derivative. I was thinking it would be easier to go ahead and multiply out the equation for y to make getting the derivative just real fast. So when I look at that, the derivative, y prime, would be negative 2x minus 2. Now, I need to find critical values. To find critical values, you're going to set the first derivative, f prime of x, equal to 0, and also look to see if the first derivative can ever be undefined. Critical values occur when f prime of x is 0 or when f prime of x does not exist. Well, y prime is just a line, so I don't have an issue with it not existing. Like if I had a fraction where the denominator was 0, then that would be a point where the derivative doesn't exist. Not my issue here. So the only thing I need to do is set the derivative equal to 0 and solve. So when I solve it, negative 2x equals positive 2, x equals negative 1. So I only have one critical value, and the one critical value is that x equals negative 1. So now what I do is I proceed to make a sign chart. And on my sign chart, I'm going to put any critical value and make that a division. And just like with all sign charts, you want to pick some test values. So I'm going to pick a test value that's clearly to the left or lower than negative 1, and one that's clearly to the right or greater than negative 1. And if you can pick 0, I would, just because it makes it so fast to plug in. So I am going to now say I need to look at f prime of x, and then I'm going to make inferences about f of x. So I'm creating a fancy sign chart. Tomorrow we'll do the same thing, but we'll do that with f double prime of x. So if I plug negative 10 into, be real clear about this, we're plugging into the first derivative because this is a first derivative test where I build my sign chart from the first derivative. Okay? So when I plug into that first derivative, if I plug negative 10 into y prime, negative 2 times negative 10 would be positive 20. 20 minus 2 is 18, and that's positive. When I plug 0 in, y prime is going to be 0 minus 2, which is negative. And then remember, the inference you make is that if the derivative is positive, the original function's increasing, and if the derivative is negative, the original function's decreasing. So now you've done the work, it's just time to start answering questions. So if I said, where is f of x increasing? You could simply look at your sign chart and say f of x is increasing where you've got this arrow that's heading upward. F of x is increasing on negative infinity to negative 1. F of x is decreasing where you've got the downward arrow on negative 1 to infinity. Now before I go on, take a look at what you'd already said, and it matches. I'm saying that f of x is increasing right here on negative infinity to negative 1. Those match. Decreasing on negative 1 to infinity. Those match. So now what you already could see from the graph that they gave matches the algebra that we're doing. Okay, so from here, what do? Well, I need to answer about where the maxes and mins or the local extrema occur. Local extrema can only occur at critical values. Well, I've only got the one critical value. So x equals negative 1 is a critical value. It may or may not be a local max or min. But since the graph goes up and then goes down, do you realize that that means that we're going to get a max? So I'm going to say I've got a max at x equals negative 1. And on the AP exam and on my tests and quizzes, sometimes I'll just say find the x values where the extrema occur. Sometimes I want you to name the maxes and mins as points. So if I just said find the x values, you're done. But if I want you to name the points, then you've got to right quick go, wait a minute, I need the y value that goes with negative 1. So whenever you need y values, remember, don't plug into y prime. Y prime gives slope values. Plug into the original equation to get y values. So f of x always returns y values. F prime of x gives you slope information. So if I plug negative 1 in to that, negative of negative 1 plus 1 squared, that's just going to give you 0. Okay? So what that tells me is that the max is at x equals negative 1, or I could say at the point negative 1 comma 0, which I got for my y value. So I could answer the max as the x coordinate of the max or as the point that is the max, either one. Just depends on what the question asks as to how you should answer. And if you do look at the picture in the book for number 4, you should actually see that max point at negative 1, 0. So the algebraic work we do matches the book's picture that they were nice enough to give you. So what I'm doing is I'm showing you what to do when you don't have a picture and it's not just right there in front of you. So we're going to do the same thing on number 6. Number 6 says f of x equals x to the fourth minus 2x squared. So on this one, the first thing I need to do is find f prime of x. When I do f prime of x, I'm getting 4x cubed minus 4x. Now, you find critical values whenever f prime of x either does not exist or is equal to 0. F prime of x is a cubic function. You don't have any issues with it not existing. Like you don't have holes in the graph, you don't have vertical asymptotes, you don't have any of that going on. So the only thing you've got to worry about is when the first derivative equals 0, because f prime of x does not exist, it's just not going to happen. Well, if I'm going to solve this equation, I'm going to factor out the GCF. Oh, and then look, I can factor again into x plus 1, x minus 1. So when I solve the equation, I'm going to have x equals 0, negative 1, and positive 1. So what I'm saying here, guys, is you've got 3 critical values. If we've got 3 critical values, then let's proceed. Our sign chart's going to be bigger. So put your critical values on the sign chart in the correct order numerically from small to large. So I'm going to create my divisions. And I'm going to get some test values here. So I'm going to choose maybe negative 10, negative 1/2 or negative 0.5, however you want to think about that, positive 1/2 or positive 0.5, and then positive 10. So from there, I need to plug into f prime of x. And then from there, I'll make inferences about f of x. So these are the kind of fancy T-charts that you're going to be, not T-charts, but sign charts, that you'll be drawing for me on the quiz and on the AP exam if you're taking it. Excuse me. So remember, to get your positives and negatives, you want to plug into f prime of x and plug into the simplest form you've got for f prime of x, which would be the factored form if you want to make it really, really quick. So when you plug in negative 10, this 4 times negative 10 would be a negative. Negative 10 plus 1 would be a negative. Negative 10 minus 1 would be negative. 3 negatives will produce a negative answer. Plug in negative 1/2. 4 times negative 1/2 is a negative. Negative 1/2 plus 1 would actually be positive. Negative 1/2 minus 1 would be a negative. 2 negatives make a positive. Plug in a half. So 4 times a half is positive. 1/2 plus 1 is positive. 1/2 minus 1 would be negative. So I get one negative answer, makes a negative result. Plug in 10. So that would be positive 40, positive 11, positive 9. You don't need the numbers, just the signs. 3 positives make a positive. Now, let's figure out what's going on with f of x. So if f prime is negative, f is decreasing. If f prime is positive, f is increasing. If f prime is negative, f is decreasing, and f is increasing. So the arrows, if you draw them to where they're going from the left to the right side in the correct decreasing, increasing shape, you basically have a little jagged sketch of f of x. Now we need to smooth it out and put it on the right points and so forth on the x-axis. So I need you to answer where f of x is increasing and where f of x is decreasing. So f of x increases on, so it's going to increase where your arrows go up. So I'm looking at negative 1 to 0, union 1 to infinity. Does that match what we did originally? Negative 1 to 0, union 1 to infinity. Hot dog, we've got that. F of x decreases on, down arrows would be negative infinity to negative 1. Union, down arrow 0, 1. And I see that that matches what we originally answered when we just looked at the book's graph. So again, what I'm doing, you might say, why are you doing all this? We already know all the answers. Because what we're going to try to do is begin to create graphs based on this information rather than just reinforcing what we've already seen on a graph. So I'm just trying right now to show you that what you've already seen graphically matches the algebra that I'm teaching you. So now it's time to talk about maxes and mins. And look, do you see if the graph goes down and then up, this would be the site of a min. If the graph goes up and then down, I create a max. If the graph goes down, then up, I create a min. So I can say that I've got a max at x equals 0, and I've got mins at x equals, it looks like -1 and x equals +1. So if all I ask you was to name the x values at which the extrema occur, you're done. If I actually asked you to name the points that are the maxes and mins, then we've got to plug in. So remember, when you plug in, you plug into the original f of x. It's the original f of x that spits out y values. So if I right quick said, okay, wait a minute, let me do some scratch work. F of 0 is going to be 0 minus 0. F of -1 is going to be -1 to the 4th. -1 squared is still 1 minus 2, so that's going to be -1. F of +1 is going to be 1 to the 4th minus 2, so that's also -1. So I would say, okay, that means I've got my max, if I had to name it in point form, at 0, 0. And I've got mins at -1, -1, and +1, -1. And if you'll right quick look at the graph, does my purple algebraic work match what you're seeing on the graph from the book? So again, my goal is to try to get you to put together the algebra with what you've already identified graphically. So we're trying to get those two ways of thinking about things to come together for you. So let's go through the whole spiel, which you're going to be doing lots of this on number 7. So I'm looking at number 7 and seeing that the equation is that f of x equals 1 over x plus 1 squared. And I choose to rewrite it as x plus 1 to the -2. And I'm only doing that because it seems like to me, since I've got to do f prime of x, that would make it pretty quick using chain rule. So f prime of x equals -2, x plus 1 to the -3, times the derivative of the inside, and the derivative of the inside is just 1. So let me rewrite that in a good way, and that would be -2 over x plus 1 to the 3rd power. Are you all right there? Okay, so now we need to figure out, where is f prime of x equal to 0? Where does f prime of x fail to exist? Because that's the way I find critical values. Well, on this fraction, the only way the fraction could equal 0 would be if the top equals 0, and -2 is never going to equal 0. So f prime of x equals 0 is not going to have solutions, so no critical values from there. F prime of x does not exist if the bottom equals 0. So the bottom does not equal 0 if x is equal to -1. That would make the whole bottom go to 0. So x equals -1, I'm going to say is loosely a critical value. And you might go, loosely? What do you mean by that? Well, the reason I say loosely is critical values have to be in the domain of the original function. And -1 is not in the domain of the original function. So very technically, it wouldn't be a critical value. But if you're going to figure out where the graph is increasing and decreasing, you still need to look at it as a critical value on the sign chart. So I still have to flow through the rest of this business. So I would basically say, yeah, we're going to act like x equals -1 is a critical value, but in a very strict sense, it's not. But we still need to go through and do the work if we're going to graph. And you don't graph on this one, but that's where we're headed. So I want to look at it. if I build the sign chart, there's something about this I'm wanting you to see because I want to reinforce an idea with you. So on the sign chart, I've got maybe negative 10 and 0, kind of like I did on the first one. Let me look at f prime of x, positive, negative. Let me look at f of x, increasing, decreasing. So if you plug negative 10 into f prime of x, I would have negative 2 on the top. Negative 10 plus 1 is negative 9 cubed is negative on the bottom. So I would have a positive result. So f of x increases. If I plug in 0, I've got negative 2 on the top. And 0 plus 1 cubed is positive. So wait a minute. I've got that the graph is increasing and then decreasing. So if all you do is think, oh, well, that means I'm going to have a max, and you don't think about that little tricky thing I mentioned a second ago, then you're going to misfire. You're going to say that there's a max at x equals negative 1. But guys, look at the picture in the book. Is there actually a max at x equals negative 1? And you should be going, oh, no, there's not. In fact, there's a vertical asymptote at x equals negative 1. So this is not a max. That's not true. And the reason is, if I go back to that very strict definition, since there were no critical values, there can be no maxes or mins. The only time you can have a max or min is if you look at the pool of critical values. So that's a little sticky wicket, but it is something that you need to know. But I can still tell, even though there's not a max or min, I can still get back to the question about the increasing, decreasing. And so the table does reinforce that the graph increases on the up arrow, so it's on negative infinity to negative 1, which does match what you had seen from the original graph. And the graph does decrease on down arrow, negative 1 to infinity, which does match what you had already seen. So my point is, even without having the graph of f of x, I could have figured out algebraically from my sign chart where f of x was increasing and decreasing. So this algebraic process will allow us to figure out what the graphs of f of x look like if we're not already familiar with them. I'm going to skip this slide now that we've done it. So let's go ahead and do the same process for a brand new function. And then we're going to stop and we're going to look at some things in a different way. So g of x is given. It says factor g of x and make a quick sketch of the function. So when I ask you to do something like this, what I'm asking you to do is, before we get bogged down in all the calculus stuff, think about what you already know from Algebra 2 and pre-calculus. So if I factor g of x, I'm going to factor out a 1/4 x as a GCF. So that's going to leave me x squared minus, and I think I'm going to have a 4th of 32 to give me the 8x. I'm double checking 1/4 x times x squared is 1/4 x cubed. Ding. 1/4 x times negative 32 is negative 8x. All right, so I've got that. Now that doesn't factor further. It says make a quick sketch. What I can do with this is, do you see that I can see, because of the factored form, that the roots of g of x are going to be at 0 and at plus or minus the square root of 32. So if I wanted to be really, really good about that, I would say 32 is 16 times 2, so 4 square root 2. Now, my really quick sketch indicates that, let's see here, square root of 32 is going to be a little bit smaller than the square root of 36. So the square root of 32 must be 5 point something or other. So I'll put it somewhere between 5 and 6. Boy, I'm batting 1,000 here, having to kind of work that in. And I know if it's a cubic function and the 1/4 x cubed is positive, that it's got to be up on the right, down on the left. This is not a good sketch. But that would be the most of what you had to do on the sketch when you were in pre-calculus. You would have stopped right there. You wouldn't have worried about maxes and mins. We would have called it a day. Now, we're going to go beyond this basic red graph and make it better now that you're in calculus. So the next thing we're going to do is find g prime of x and identify critical values. How do you do that? Well, g prime of x you know how to do. That's going to give you what? 3/4 x squared minus 8. How do you identify the critical values? Look at where g prime of x equals 0, and also look if g prime of x does not exist. So first I'm doing the 3/4 x squared equals 8. X squared equals 32/3. So x equals plus or minus the square root of 32/3. Well, what a nice number. I'm going to leave it like that. I'm not going to get any better than that. That's a decent, yeah, I could simplify and then get the radical off the bottom, but since I'm not here, just let me leave it right there for the time being. Now, does g prime of x ever fail to exist? No, you don't have a fraction that's going to create asymptotes or holes in the graph. So that means your only critical values are where g prime of x equals 0. So I've taken care of that part. Now, if you want me to be more specific and be a good little algebra student, I know 32 is 4 square root 2 over the square root of 3, multiplied by the square root of 3 over the square root of 3, so I get 4 square root of 6 all over 3. So that's how I'm going to handle a better looking critical value. Next step then is to use a sign chart to determine intervals over which the function increases, decreases, and to find the extrema. We've done this part. So my critical values are negative 4 square root 6 all over 3 and positive 4 square root 6 all over 3. And you might be thinking, arg, are we going to have to do this on no calculator part of the test? Well, yeah, probably. But don't sweat it. You know 0 is going to be between them. Now, I'm not totally sure the value of 4 square root 6 over 3, but I'm pretty daggum sure that those are not as big as like 20. So one thing you can do to speed you up is just pick like outrageously big critical values, test values I should say. Then you don't have to worry about picking something. Well, can I pick 1? Can I pick 2? Just go big and then it doesn't matter. So I'm going to plug into f prime of x. G prime of x. I'll fix that. There you go. Sorry about that. Don't want to confuse you by not calling things clearly. So g prime of x I never really did simplify, so I'm just going to plug it in as is. Well, guys, I know negative 100 quantity squared is positive. And if I divide 100 by 4, I get 25, and 25 times that 3 would be 75. 75 minus 8 is positive. So since I've picked really big, well, I was actually plugging in 10 squared, but since I plugged in really, really, really big test values, the signs are going to be real clear. If I say g prime of 0, I get 0 minus 8 is negative. That's an easy one. You can do that without a calculator. When I plug in 100, I'm going to get 100 squared. It's huge. 3/4 of 100 or 3/4 of 100 squared is still huge. Minus 8 is definitely positive. G of x must then be increasing, decreasing, increasing. So notice when I look at this, it's telling me my graph goes up, down, up, which follows the red graph that you originally did just using your pre-calculus skills. If I ask you specifically to name increasing and decreasing, do. But a lot of times what I'll just say is show it on the sign chart. So I can see here that g of x increases on negative infinity to negative 4 square root 6 over 3 union 4 square root 6 over 3 to infinity. G of x decreases between the negative and positive 4 square root 6 over 3. So generally, if you've showed the arrows correctly on the T-chart or the sign chart, I don't make you write all that out again. Now, the local extrema. Do you recognize that this would have to be a max and this would have to be a min? So I can say that I've got a max at x equals negative 4 square root 6 over 3, square root 6 over 3, and a min at x equals positive 4 square root 6 over 3. But what I want to do is I want to get a really good graph that's more specific for f of x. And I'll let you find the y values on your calculators. So let's plug 4 square root 6 over 3 into your original g of x. Okay, so we need to find y values. When I do g of negative 4 square root 6 over 3, give me a minute. I'm button punching. I hope you are too. I've done something goofy. Sorry about that. I just realized that everything I was entering, I entered on the wrong screen. That was great. Sorry about it, because I know you don't want to have to just sit here waiting, but hopefully this has given you plenty of time to get this. I'm trying this again and trying to fix my mistake. All right, finally, I'm getting on this one 17 point, if I'm plotting, 419. If I'm plotting, I'm just going to plot roughly 17.4. Let me do g of positive 4 square root 6 over 3. I'm going to show you something when I get back with the calculator that might help you move a little bit faster on this part. It's actually what I'm doing right now that I quit messing it up. Yeah, I'm getting negative 17.419. So if I said name the max, you would say the max point equals the negative 4 square root 6 over 3, comma 17.419. And the min equals negative 4 square root 6 over 3, comma 17, negative 17.419. So the function seems to be odd because opposite x's are producing opposite y's, which is what I would have guessed just from my little baby red graph from pre-calculus. So I found the local extrema. I did that in blue. So what we're going to do is we're going to go back and refine the graph. And we'll work much more with this tomorrow. But I would say, I'm going to do that up here. I would say, here's what I know. I've got 1, 2, 3, 4, 5, 6. So I'm going to 1, 2, 3, 4, 5, 6. I'm going to use the root information that I found pretty easily just from my pre-calculus or algebra 2 skills. Now I'm actually going to say I need to plot these 2 points. So negative 4 square root 6 over 3. If I say, let me take the square root of, I'm getting that those are at roughly 3.3. And if you, well, forgive me here if I say this is 17, this is 18, This is negative 17. This is negative 18. So this point is roughly negative 3.3, comma 17 point whatever. And then this point here is positive. I just realized what I wrote. Sorry. Positive 123.3, comma negative 17. So you plot those points very, very, very specifically, and then you make your graph. So your graph is roughly just like the red graph, except now I've got it specifically going to the correct max and min. Now, tomorrow, when we do the second derivative test, you're going to layer on another detail that's going to help your graphs be even more specific. All right, let's see what we can do on this one. And tell you what, stop video 1, take a breather, maybe 2 minutes, and then restart video 2. This will be a good stopping point.